Hi everyone. In this video, I'll be covering faster RCNN, and this one will be focused on the implementation part. If you don't know about faster RCNN or want to review some of its details, I would suggest to first watch the previous video of this series before going ahead with this one. The plan for this video is to first build a simple version, right from anchor generation, RPN, ROI layers, all the way up to the complete faster RCNN module, understanding everything in detail. We will then walk through the entire PyTorch faster RCNN codebase and cover all the components that are involved in it. In the end, we will train both the versions on VOC 2007 dataset. The one we implemented will be trained from scratch, and for the one using PyTorch faster RCNN codebase, we would be fine-tuning a pre-trained faster RCNN model. We will see detection results after training on VOC dataset for both of them. This will be a two-part video. In this one, we implement a simple faster RCNN module, and in the next video, I'll cover the PyTorch faster RCNN code walkthrough. Let's start with building an implementation. For this one, what I've done is taken the different parts from PyTorch codebase, gotten rid of all the abstractions, and modified them to cater to only a batch size of 1 and single scale feature map, as that makes the implementation relatively easier to understand. By the end, we would have created faster RCNN with VGG16 with all the core functionalities. And this will make the next part of understanding PyTorch faster RCNN codebase much easier, as that is just everything we'll implement plus catering to greater than one batch size and feature maps of different scales. So let's go. To remind ourselves, faster RCNN has a backbone, RPN specific layers, and ROI specific layers. We will create 3 modules for this: RPN module, ROI head, and a faster RCNN module, which will be our faster RCNN model. Faster RCNN model will first call the backbone to get the image feature map, and then it will call RPN to get proposals for this image. Inside RPN, we'll first call RPN specific layers, and then generate anchors according to the image and feature maps tried. Convert these anchors to proposals using the box regression predictions, and compute RPN classification and localization loss based on the ground truth boxes and labels. RPN will return the proposals for the image and both the RPN losses. Faster RCNN module will then call ROI module with these RPN generated proposals. Inside ROI head module, we'll perform ROI pooling and then pass the pooled features for RPN generated proposals to FC layers, including the classification and box regression FC layers. Using the box regression predictions, it's going to transform RPN generated proposals to prediction boxes. And based on the ground truth boxes and labels, it's going to compute the detection losses. Finally, ROI head will return the prediction boxes and the detection losses. And faster RCNN module is going to return these predicted boxes and the RPN and ROI losses for us to backpropagate from. Faster RCNN module will receive 2 inputs: image, which will be B cross C cross H cross W tensor, but we'll only work with batch sizes of 1, so it will be 1 cross C cross H cross W. The second one would be targets, which will be a dictionary containing 2 keys: bounding boxes, which is the tensor containing coordinates for the ground truth boxes for the image, and labels, which contains the class indexes for the ground truth boxes. RPN and ROI head will additionally receive the backbone feature map as well. We will first create RPN, which will take the feature map as input and generate proposals for the given image. And it will do this using a 3x3 convolutional layers and 2 sibling 1x1 convolutional layers. These 1x1 convolutional layers will be generating predictions for anchor boxes in the image. Specifically, one of the layers will generate classification scores and will have 2K channels. So foreground and background probabilities for the K anchors at each location. The other will generate 4 transformation parameter predictions for the k anchors at each location, hence 4k channels. In our implementation, instead of predicting 2 classes and a softmax, we will just predict one value as the foreground probability. So we'll just have k channels and a sigmoid activation after the classification layer. RPN will be taking these anchor boxes and generating proposals by classifying these anchor boxes as to whether they contain an object or not, and modifying the anchor boxes so that they tightly fit the object that they contain. And the entire RPN would be trained using a combination of classification loss on these anchors and localization loss on the positive labeled anchors. Now let's implement the RPN part. We'll create this region proposal network module for RPN. As argument, the only thing it will take is the input channels present in the feature map output of backbone, which for our case is 512. We need to generate anchor boxes for RPN, and for that we need to specify the scales and aspect ratios for these anchor boxes. The values used by authors of faster RCNN was 128, 256 and 512 for scales and 0.5, 1 and 2 for aspect ratios. So each feature map cell is going to have 3 times 3 9 anchor boxes. The RPN module is only going to have 3 layers. First one is a 3x3 conv layer, and the other two are 1x1 conv layers for classification and anchor box transformation predictions. Classification layer with the output channels being k, and bounding box transformation parameter prediction layer with output channels being 4k. The forward method of RPN is going to receive the input image, feature map output, and targets, which will be a dictionary containing ground truth boxes and labels. Throughout the video, I'll keep mentioning the shapes of all of the different variables involved. These represent the state of different variables and their shapes in one of the training runs of this code. So for this instance, our RPN received a 600x800 image, and this image has 6 ground truth objects, as is evident from the shape of target boxes and labels. We first call all RPN layers, so the 3x3 and 1x1 conv layers, and get the classification scores and the box transformation prediction for all the 9 anchors at all feature map cell locations. We then generate anchors, and for this create a new method called generate_anchors, which takes the input image and feature map and returns all anchor boxes in the image. The way we do this is that we first create base anchors, which in our case will be 9 anchor boxes. These base anchors will be 0-centered and represent anchors of the defined scale and aspect ratios. Then these base anchors will be duplicated and shifted using the stride of feature map to create anchors for the entire image at all feature map cell locations. Here I just show a sample of the duplicated set of anchors belonging to only one scale and 3 different aspect ratios. But there would be a total of 9 of these, 3 scales with each having 3 aspect ratios, and they would all be aggregated together. To achieve this, we first get the image and feature map heights and widths and use them to calculate the strides in both the dimension. Our feature map is going to be the VGG16 output without the last max pooling, so stride would be 16 in both directions. Now we'll first create anchor boxes of area 1 and honoring these aspect ratios. So with h times w equals 1, an aspect ratio defined as h divided by w, which is what the PyTorch code later also uses, we can see the height of these unit area anchor boxes will be the square root of aspect ratios, and their width will be 1 divided by height. Because these are dimensions for area 1, to get anchors of different scales, we can simply multiply the width and height with all these scales. This will give us the width and height of all the 9 anchor boxes. We then create zero-centered base anchors for all of them. So this base anchor will be of shape 9 cross 4, and as for this particular instance, these would be the base anchors. You can see that the aspect ratio of the first 3 boxes are 1:2, then the next 3 are 1:1, and the last 3 are 2:1. And in each set, the first box is of 128 times 128 square area, second of 256 times 256 area, and third of 512 times 512. Now we will convert these base anchors to a grid of anchors, capturing all possible locations of the feature map. Basically, we will compute a grid of shifts that need to be applied to this base anchor to create the grid of anchor boxes. The shifts will be stride h apart in y-axis and stride w apart in x-axis. This is because anchor boxes coordinates are with respect to the image. And since every feature map cell has a set of anchors, so we'll have anchor boxes at every stride, which is 16 pixels in the original image. We create a grid from these shifts. Shift x for each location will be used to shift x1 and x2 of the base anchor to create the x coordinates of the anchor boxes at that location. And similarly, shifts y will be used to do the same for y1 and y2. And then we simply add these shifts to the original zero-centered base anchors to create all anchor boxes for the entire image. Currently, shape of anchor is feature map height times width cross 9 cross 4. And we reshape it to get feature map height times width times 9 cross 4. So in this instance, 1850 times 9 cross 4. Do note that rather than all of these anchors having their centers at the center of the feature map cell, in this implementation, which is exactly same as the PyTorch implementation, they have their centers at the top left coordinate of each cell. After generating these anchors, we reshape the CLS scores and box transformation parameter predictions to be of the same shape as that of anchors. The 1 cross 1 layers would give CLS scores of shape batch cross number of anchors at each location, as that was the channel, cross feature map height cross width. We use that to fetch the number of anchors at each location, which will be 9. Then we permute and flatten such that the CLS scores becomes batch times feature map height times width times number of anchors per location cross 1. For this we assume the batch size is 1, otherwise that would have been the first dimension, and we would get a batch size cross number of anchors cross 1 tensor. We do the same for box transformation prediction to have it as feature map height times width times number of anchors cross 4. Then we take the anchors that we generated and apply these transformation predictions to all these anchors. This will transform the anchor boxes to proposal boxes for this image. We will do this by this apply regression prediction to anchors or proposals method, a method that will be common for RPN as well as ROI layers. So this will cater to anchors for RPN and proposals in ROI layers. Because even in ROI layers, we require this functionality to transform proposal boxes using the 4 transformation parameter prediction to detection boxes. This is why we'll assume that our box transformation prediction will be of shape number of anchors or proposals cross number of classes cross 4, just to simplify the implementation. For the RPN case, number of classes will be 1. The anchors or proposals will be n cross 4, with n being the number of anchors or proposals. And this method is going to return boxes generated after transforming the input boxes based on the transformation prediction. In RPN, the output of this method call will be proposal boxes, and in ROI layers, the output of this function call would be detection boxes. The first thing that we do is for the boxes compute Cx, Cy, width and height from the x1, y1 and x2, y2 coordinates. dx, dy, dw and dh are obtained for all n cross k, where n is the number of anchors or proposals and k is classes. Again, for RPN, this is just 1. These are the transformation parameter predictions made by RPN for all the anchors. Then we compute the transformed center x, center y, width and height to get the transformed n cross k boxes. This is the same formulation that we had seen in RCNN video, except that rather than transforming px, py, pw and ph, we are transforming anchor cx, anchor cy, anchor width and anchor height. And then we get the x1, y1 and x2, y2 coordinates from these. The final output will be of the same shape as box underscore transform underscore pred, which was n cross k cross 4. For RPN, this will be n cross 1 cross 4 proposals. And for ROI head, assuming 21 classes for VOC dataset, this will be n cross 21 cross 4 prediction boxes. Then we call this method to get proposal boxes from the anchors and the transformation parameter predictions made by RPN. Here we do a detach because for detection layers, we are going to treat proposals as pre-computed and fixed. In order to use these proposals for ROI layers, we do a bunch of filtering and modifications in RPN, all of which happens inside this filter underscore proposals method. Specifically, we first select only top k scoring RPN proposals, and here I am using k as 10,000. We then clamp these proposals to be within the image boundary. Basically, with the generated proposals and image sizes provided as argument, we ensure via clamping that proposals x coordinates are always between 0 and width and y coordinates between 0 and height. The PyTorch implementation also removes boxes of low area here, but I don't have that in this implementation. However, it's there in the code that is provided in the repo. Then we perform NMS with a threshold of 0.7. And finally, out of all the boxes that remain, we get only top 2000 highest scoring proposals, for which we sort the NMS retained indexes using their classification scores. Filter underscore proposals returns the top 2000 proposals and their CLS scores. In the actual implementation, we'll have different numbers for the top K values, depending on whether we are in training or inference. But here I'm just using 2000 for both. If we are in inference mode, then this is all we need from RPN. The proposal boxes and their scores, that's it. But if we are in training, we need to assign ground truth labels to these anchors and compute classification and localization loss using the predicted and target classification scores and box transformation parameters. So this method will do exactly what the name suggests: assign targets to anchors. For this instance of run, there are 6 ground truth boxes in the image. So GT underscore boxes will be 6 cross 4. Again, we go with the assumption that it's a batch size of 1. Now for assigning targets, we need to compute IOU. So let's create this method get underscore IOU, which given boxes 1 of shape n cross 4 and boxes 2 of shape m cross 4 will return the IOU matrix of shape n cross m. And we'll be calling this with ground truth boxes and anchor boxes. So each cell I, j of the output will represent the overlap between ground truth box I and anchor box j. We have already implemented this in our MAP video, but only for a single pair of boxes. And here we are just expanding that implementation for 2 groups of boxes, but the core implementation is the same. We fetch the areas of each of these boxes, which will be x2 minus x1 times y2 minus y1. Then for each pair, top left x1 y1 of the overlapping rectangle will be the maximum of x1 y1 coordinate of the 2 boxes in that pair. And similarly, x2 y2 of the overlapping rectangle will be the minimum of the x2 y2 coordinate of these 2 boxes. Intersection area is just the product of these 2. And to get the overlap, we just do intersection divided by union. Now back to the ground truth assignment. The IOU matrix will be of shape number of ground truth boxes cross number of anchors, which for this case would be 6 cross 16,650. Max along the dimension 0 will give us for each anchor boxes the IOU value and the ground truth box index amongst the 6 ground truth boxes that has the highest IOU with that anchor box. So each value of ground truth box index will be from 0 to 5, as there are 6 ground truth boxes. We create a copy of this because if you remember in the paper, the authors mentioned that in order to ensure that we always get positive anchors, for each ground truth box, we also add anchor boxes which have the highest IOU with that ground truth box, even if its overlap is less than the foreground threshold. So we'll be updating these assignments later, which is why we have kept a copy of these ground truth box indexes prior to modifying it. Then we get all the below 0.3 threshold anchor boxes, so those which have the maximum overlap less than 0.3, and these will be our background anchors, and also those for which the maximum overlap with any ground truth box is between 0.3 and 0.7 will be the anchors that we will ignore. The best match ground truth index, which up till now was 0 to 5, will be updated as -1 for these background anchors and -2 for all the anchors that we want to ignore. Now we add positive anchors based on the other condition. So we go back to the IOU matrix and this time max along the dimension 1, which means for each ground truth box, we are finding the maximum IOU value which this ground truth box has with any anchor. Then we take this best anchor IOU value for the ground truth box I, and from our IOU matrix, we get all the anchor boxes which have this same overlap value with the ground truth box I, and do this for all the ground truth boxes. Which means if, for example, the ground truth box at the 0th index has the value of maximum IOU as 0.4, then this will give us all the anchor boxes which have overlap equal to 0.4 with the ground truth box 0. So essentially we are getting ground truth box and anchor box pairs that have maximum IOU between them. As a hypothetical example, if this is the returned value of this ground truth prediction pair with highest IOU variable, then this means the 8894, 8905 and 8914 indexes are the anchor boxes that all have maximum IOU with the ground truth box 0. And the remaining 3 are anchor box indexes that all have maximum IOU with the ground truth box 1. So from this we extract those anchor box indexes which are low quality positive anchor candidates and update the ground truth box indexes of those. So what will happen here is that some of the anchor boxes for which the best match ground truth index was marked as -1 or -2 because it was less than the 0.7 threshold, some of them will now be modified with a valid ground truth box index. And this is why we had copied the best match GT index variable prior to thresholding. This was all that we needed to do additionally for low quality boxes. Now in order to set regression targets for these anchors, we need the coordinates of best matching ground truth box. But as of now, best matching ground truth index has -1 and -2 values as well. So we get matched ground truth boxes as this. Matched ground truth boxes will be of the same shape as anchors. And because of clamping, this means that all background and to be ignored anchors will be assigned to the 0th ground truth box. And this is fine because we'll be filtering out those using labels later. We'll create labels such that for foreground anchors, label will be 1, for background, label will be 0, and for anchors that we want to ignore, label will be -1. Then later for classification loss, we'll filter anchors by labels greater than equal to 0, and for localization, we'll filter by label greater than equal to 1. So let's create those labels. Now back in our forward method, we'll call this and here for the ground truth boxes, I'm simply passing the 0th value, again with the assumption that we are always going to have a batch size of 1. Now we have anchors and their assigned ground truth boxes and labels. Then we get the target transformation parameters for all anchors based on this assignment to compute the localization loss later. For this also, we'll have a single method for both anchors in RPN and later for proposals when we are implementing ROI layers, which will be this boxes to transformation targets method. Because detection part also has a localization loss, which requires the same kind of target computations. Just that at that time, we'll have proposal boxes instead of anchor boxes. This is also the same as what we had seen in RCNN video. And we need center X, center Y coordinates, as well as width and heights of both anchor boxes, which is P in the formulation here, and ground truth boxes, which is G. We first get the width, height, center X and center Y for all anchors or proposals from the x1, y1 and x2, y2 values. The same is then done for the ground truth boxes. Then we use the transformation parameterization to compute the target values which the 1x1 regression convolution layers is supposed to predict for each anchor box. And in the case of ROI layers, what the bounding box FC layers is supposed to predict for each proposal box. After stacking the 4 targets, regression targets will be of the same shape as number of anchors or proposals cross 4, as there are 4 transformation parameters. And then in the forward method, we'll call this and get the desired targets for all anchor boxes. As of now, we have 16,650 anchor boxes. But remember, we don't use the entire set of anchors for training. Rather, we sample from them. And again, this is also something which we'll need in ROI layers as well, because we'll not train from all the RPN return 2000 proposal boxes. Rather, only a sample of them will be used for training. So again, we'll create this common method. We provide this method labels, positive count, which for RPN will be 128, and total count, which for RPN would be 256. So essentially, this method would sample 256 anchors such that 128 from them is positive and the remaining 128 are negative. Positive anchor indexes are those with labels 1. This greater than equal to 1 ensures that the same method can be later used for ROI layers as well, as during that call, labels for foreground proposal boxes will be between 1 to the number of classes minus 1. Background are those with labels as 0. We first sample as many positive as we can, and if the desired count of positives is not reached, we sample extra negative anchors. Select randomly the desired number of positive and negative anchor indexes. And finally, this method returns 2 Boolean masks. One where the indexes belonging to the sampled positive anchors are true, and the other where the indexes belonging to the sampled negative anchors are true. Both these masks will be of the same shape as labels. Now we will compute the losses using these sampled masks. For classification, we will use all the sampled indexes. So here we are getting those which were either selected as positive anchors or negative anchors. Then we compute the localization loss, which is smooth L1 loss, using the sampled positive anchors. And classification loss is just binary cross entropy between the classification scores and labels of the sampled indexes, both positive as well as negative. So in training, we'll compute and return the losses in addition to the scores and proposals that we computed earlier. Whereas in inference, we just return the proposals and scores. This brings us to the end of RPN implementation. Let's summarize everything that we did for RPN. There were some steps we did for both training as well as inference. These were calling the RPN layers, generating anchors, converting these anchors to proposals, using the transformation parameter predictions for these anchors, and finally filtering proposals to only pass these filtered proposals to the next ROI layer. For inference, this is all that we need to do. However, if we are in training, we additionally need to assign ground truth boxes to these anchors. Using these assignments, compute their classification and regression targets, which the 1x1 convolution layers are supposed to predict. Sample positive and negative anchors, and for all the sampled anchors, compute classification loss, and for the sampled positive anchors, compute the localization loss. Next, we'll get into building the ROI head, which will have all the detection specific layers. The ROI head module will have two arguments: number of classes, which for VOC dataset would be 21, including background, and channels of feature map, which is 512. Pooling output size will be 7x7, and the FC layers will have a dimension of 1024. FC6 layer is going to take the pooling output, which will be number of channels times 7 times 7, and convert that to 1024. FC7 is another linear layer of 1024 x 1024 weight matrix. And our prediction layers are two FC layers, one for classification, with output size being the number of classes, and the other for regression, for which the output is going to be the number of classes times 4. The forward method would receive the feature map output of image, proposals returned by RPN for this image, shape of the image, and target dictionary. The shape of proposals for this instance will be 2000 x 4, but it can be less than 2000 as well, because it could be that NMS in RPN leaves us with less than 2k proposals. And obviously, had we catered for larger than one batch size, there would be a batch dimension in here as well. So here also, if we are in training, we need to assign ground truth labels to these proposals. And assuming a batch size of 1, we get the ground truth boxes and ground truth labels. The PyTorch code, even before assignment, first concatenates ground truth boxes to proposals as well. So this way, even if our RPN is generating lower quality proposals, leading to no positive proposals, ROI head will still get an opportunity to learn to classify foreground classes correctly, because these added ground truth boxes will obviously be labeled as foreground class proposals. This part is there in the repo code, but in here I don't do that. To assign targets, we create this assign target to proposals method, which is exactly same as assign target to anchors that we implemented in RPN. Except it does not have the additional responsibility of adding low quality boxes. So we get the IOU matrix, perform max to get best ground truth index for all proposals, set the best matching ground truth index to be -1 for background proposals, which are those with less than 0.5 IOU. Then we clamp and get the matched ground truth boxes. And then set labels for these foreground proposals as the label for the matched ground truth box. And for background proposals, the label is 0. The returned labels and matched ground truth boxes for these proposals are of shape 2000 and 2000 x 4 respectively, since that is the number of top scoring proposals that our RPN returns. Then we use the same sampling method that we created for RPN to get positive and negative sample masks for these proposals. The only thing that changes is the size of sample and the count of positive proposals. After keeping only the sampled proposals, labels and their matched ground truth boxes, we are only left with 128 proposals rather than 2000. We then get the regression targets for each of these proposals using their matched ground truth boxes, and again reuse the same method that we had created for RPN. Now for these proposals, we'll get their features using ROI pooling. ROI pooling during inference will be performed for all proposals, but during training, it will only be performed for the sampled proposals, which is 128 for this case. For ROI pooling, we need to pass the spatial scale as argument. This is nothing but the fraction of feature map height width and image height width. So how much downscaled the feature map is. This would be needed to map the proposal coordinates on the feature map for the ROI pooling implementation. For our case, we are going to use VGG16 with the last max pooling layer removed. So stride of 16, meaning 1 by 16 is the spatial scale. Then we simply call the Torch Vision's ROI pool method with the feature map and proposal boxes. The ROI pooling output would be number of proposals cross 512, as that was the channels, cross 7 cross 7. So we flatten the first dimension to get 25088 dimensional feature for all the 128 proposals. And obviously during inference, this would be say 2000 cross 25088. Post that, we call the FC6, FC7 and CLS and regression FC layers. Classification scores would be 128 cross 21, as we have 21 classes, and bounding box transformation predictions would be 128 cross 84, 4 transformation parameter predictions for each of the 21 classes. We then reshape the box transformation predictions to be 128 cross 21 cross 4, so number of proposals cross number of classes cross 4. This FRCNN output will be the output that this ROI head will return. And if we are in training, this will just be the losses. But if we are in inference, this will instead be the predicted boxes, their scores, and their class labels. Let's do the training part first. Classification loss will be cross entropy between the logits for classification scores and the ground truth labels for these proposals. For localization, again, we'll just use the foreground labeled proposals. And remember, our background proposals had a label of 0. For these foreground proposals, we fetch the ground truth class. Then localization loss is the smooth L1 loss between transformation predictions made by the box regression FC layer for this ground truth class and the target transformation parameters that we had computed for these proposals. And as I had mentioned, if we are in training, then this is what the output of ROI head will be, just the losses. But if we are in inference, then we need to convert these proposals to prediction boxes and perform some filtering after that. So let's see all of that. Using the computed transformation predictions, we first modify these RPN generated proposal boxes to prediction boxes. This is the same method which we created for modifying anchor boxes based on their transformation predictions in RPN. Only difference is that when we called for anchors, the second dimension, which was number of classes, was 1, but now it will be 21. Now since this part of the code will be called during inference only, it would have 2000 proposals as input rather than 128, as we won't be doing any sampling during inference. But since we have been keeping track of shapes for these sampled 128 proposals, let's just continue with that assumption that even in inference at this point, we only have 128 proposals rather than 2000. Then prediction boxes will be of shape 128 cross 21 cross 4, and prediction scores will be of the same shape as classification scores, which is 128 cross 21. After softmax, to convert logits to class probabilities, we will perform filtering and return these filtered boxes as predictions. First, we'll clamp all prediction boxes to image boundary, using the same method that we created for filtering in RPN. Just to ensure that after applying the predicted transformation, x1, x2 of these predicted boxes are between 0 and image width, and y1, y2 are between 0 and image height. We will now create labels for these boxes, which will be the class indexes, and ultimately have them of shape 128 cross 21. These values will be 0, 1, all the way till 20 for the 21 classes. Then we expand it to be of the same shape as classification scores, making it 128 cross 21. And we don't really care about boxes which have predicted label as background, so we just get rid of the boxes belonging to the 0th class, making the predicted boxes as 128 cross 20. Just to note what these boxes are, each of the 128 proposals would have been modified differently for different classes. That way, potentially the same proposal box can be modified to get prediction boxes for multiple classes. In fact, for each proposal box, we get prediction boxes for all classes by transforming the initial proposal according to the transformation parameter predictions for all the 21 classes. So instead of 128 prediction boxes, we have 128 times 20, which is 2560 prediction boxes. So we reshape prediction boxes accordingly. These 2560 boxes would be our set of prediction boxes on which we'll do further filtering. For this, we'll create a filter predictions method in the ROI Head class, which is going to receive these boxes, their scores, and their labels as argument. Here we'll first remove low scoring boxes. So after softmax, if any predicted box has less than 0.05 score, we'll get rid of it. Then we remove boxes which are of small size. Here I've used the threshold as 1, so if height and width both are not greater than 1, we'll also ignore such boxes. Then we do class-wise NMS, where we iterate over all the classes . For each class, we pick boxes with that class as label, call the PyTorch NMS method, and from these boxes keep only the ones which are not filtered via NMS with a threshold of 0.5. So for each class, we'll have 128 boxes, assuming no boxes have yet been filtered out. Then these 128 boxes will undergo NMS, and we'll continue updating keep_mask variable to accumulate all the boxes that we need to keep. After NMS, we sort these boxes based on their classification scores. And ultimately return only top scoring 100 detections for each image. And finally, in the forward method, we return the boxes for these top 100 detections, their scores, and their class labels, and update the FRCNN output with these new keys of boxes, scores, and labels. In training, FRCNN output just has the losses, and in inference it will have the boxes, scores, and their labels. So during implementation I messed up a bit, and everything since ROI pooling was incorrectly placed under the first if condition. So let me just fix that. So the first if condition actually should end here itself. That brings us to the end of ROI Head implementation. Let's again summarize everything that we are doing inside the ROI Head module. For training, we assign ground truth boxes to proposals, sample positive and negative proposals, and get the classification and localization targets for these sampled proposals. For both training as well as inference, we need to do ROI pooling as well as call all the FC layers, including the classification and box regression FC layers. Then for training, we need to additionally compute the losses. Whereas for inference, we need to convert the proposals to prediction boxes using the predictions for box transformation. And finally perform filtering on these prediction boxes. Now on to the final part of implementation, which will be this faster RCNN module. Faster RCNN module is going to make use of three components. Backbone, which will be VGG16 without the last max pooling layers and classifier layers. An RPN and ROI head that we just implemented. Just like the authors, we freeze the first few layers of VGG16 backbone and define the ImageNet mean and standard deviation, which we will use to normalize the input images. And the max and min size will be 1000 and 600. The way we will use this max and min size is that we'll resize the smaller dimension to be 600 pixels, but also cap the larger dimension to not be more than 1000 pixels, and maintain the aspect ratio while resizing. So whichever scaling factor is smaller, that is scaling smaller dimension to 600 or larger dimension to 1000, we'll use that scale to resize the image. Our faster RCNN forward method will just receive the image and target, which can be none in case we are in inference mode. The first thing that we have to do in forward is normalize and resize the images, for which we create this method. After applying the normalization according to the mean and standard deviation provided, we decide the scale of resize by dividing 600 with smaller dimension, which in this case is 375, and 1000 with larger dimension, which is 500. So the scale values that we get are 1.6 and 2. Whichever is lesser, we'll use that scale. Again, this ensures that if by resizing the smaller dimension to 600, we are able to keep the larger dimension less than 1000, then we'll use that. However, if that's not the case, then we use the scale that we get by resizing the larger dimension to 1000. So for this instance of sizes, we use scale as 1.6 and resize the image using that scale. Our image now becomes 600 x 800. The target boxes were for the original image dimension, which was 375 x 500. But because we resized the image, we also need to resize these target ground truth boxes. And for that, we just compute the new size divided by original size, which is going to be the scale, which here is 1.6, and multiply the box coordinates appropriately. Then if we are in training, we call this method and update the target boxes with this resized boxes along with normalization and image resize. Else, we just normalize and resize the image. Then call our backbone with this resized image. Call RPN and get proposals. call ROI Head with RPN generated proposals. And if we are in Inference, then this output will have boxes, scores, as well as labels, else it will just have the detection losses. Now these predicted boxes are for the resized image, 600 x 800 in this instance. But our original size was different, 375 x 500 in this case. So we need to resize these predicted boxes back to the original image dimension. We create this transform boxes to original size method to do that, which does exactly what we did within the normalize and resize method, that is compute the scale ratios and multiply the x and y coordinates with that ratio. Only difference is that rather than computing ratio of resized image by original size, we compute the ratio as original size by resized image. And then call this function with the predicted boxes, new image shape and original image shape. So earlier we multiplied the boxes by 1.6 and now we'll divide the boxes by 1.6. And this completes our faster RCNN class as well. And we have now implemented everything that is happening inside a faster RCNN model. We implemented RPN, ROI Head and faster RCNN module, and saw what all happens inside them in training versus inference mode. Let's quickly look at the dataset code and training code as well. This is our dataset class for VOC dataset. After creating all the classes, including background, we get the images and annotation information from the dataset XML files, where we first get some metadata and then extract all ground truth detection information for each image. Then in getItem method, we get the images and only add one augmentation of horizontal flip. In future we will add more augmentations, but for now horizontal flipping is all that I have added. PyTorch anyway provides VOC dataset class as part of Torch Vision, which will take care of all of this. I just wanted to provide the code so that you can modify it according to your dataset and try to go through it step by step. For targets, we just get the relevant information, and the only thing we need to take care of is modifying the box coordinates in case we are working with a flipped image. And again, as we add more augmentations for future methods, we'll offload all of this work to some library. For now, it's just flipping, so it's fine. The repo has model creation code that is completely configurable, so we get all necessary details to create the model from a config, rather than hard coding it like we just implemented. Then in the training script, we get this config, create our dataset and data loader, and as mentioned, we'll work with batch sizes of 1. We instantiate our model and optimizer, and in the training loop get the RPN and detection losses and optimize using the same. We could play around with different weights for combining these losses, but I just assumed all of them to be of equal weight and sum them together to compute the total loss. And during inference, FRCNN output will additionally have boxes, scores, as well as labels. Here are some of the results of training. With this implementation, for batch size 1 and single scale feature map, I was able to get till 62% MAP only. But I haven't spent any effort in tuning, and even some of the layer initialization steps, weights of the losses, using the FC layer features from pre-trained VGG16, all of those I skipped. Maybe adding those could further improve the result because the paper has an MAP of 69. So once I get some time, I'll try to experiment with all of them and update the repo accordingly. Using the PyTorch provided pre-trained faster RCNN model, I was able to get more than 75% MAP on VOC 2007 in just 5 epochs, and with loss still decreasing. So with further training and tuning, one could easily get beyond 80% MAP. And in the next video after the code walkthrough, we will see training and fine-tuning details for that. This brings us to the end of this video, in which my goal was to go through the entire implementation of faster RCNN and cover everything step by step. Hopefully, as a result of watching this video, you have a better clarity on the components that go into building faster RCNN model. In the next video, we'll go through the entire PyTorch faster RCNN codebase, understand how it handles greater than one batch size, and how it makes use of multi-scale feature map. And we'll also get into training on your own dataset using that. Thank you so much for watching this video. See you in the next one.